one of the first questions you should ask yourself when you see a rock in the field or perhaps on the side of the road or in a drill core is, how old are these rocks? And there's a few ways that we can answer that. And I guess the idea behind a lot of what we do in answering that question is by adhering to some common principles of the relationships between these rocks. And the idea being that the deeper rocks were deposited first, generally speaking, and slowly more and more layers are built up on top of these bottom layers, and so we get these progressively younger rocks. But getting an absolute age on perhaps ancient muds and ancient sediments can be a little tricky to do, especially when these rocks are really, really old, and so there aren't many dateable artifacts around like ashfall layers or lava flows, something that we can date. So one of the ways we can do this, one of the ways we can get an absolute age on our rocks is simply by looking at dateable sites from around the world and correlating them using some sort of a common denominator between the two sites. And a good example of that is something like global ocean chemistry or global atmospheric composition, something that's kind of uniting between the two fields. And when we do this, we can actually correlate rocks across broad areas and sometimes even continents. And so I guess what this kind of looks like is we look at there might be a subtle change in the ocean chemistry for whatever reason, and we should be able to sort of detect that across both sites because the ocean and the atmosphere, they're well mixed. And so we essentially wiggle match, and we finally can kind of say, okay, these rocks over here were being deposited at the same time as the rocks over there. And there was a dateable site over there, so therefore that age must be the same as this age over here. And so slowly we can piece together, I guess, the relative ages of these sites all across the world. A good example of what this kind of looks like and what we can do by correlating rocks is the discovery of the snowball Earth. And so what this was back in the sort of late 90s, early 2000s, geologists were looking at these glacial rocks all around the world, a very distinctive type of rock. And they were going, this is interesting. It looks roughly like these glacial sediments were being deposited at sort of similar ages. You know, were we seeing some rapid glaciations perhaps? But when they took a really closer look, when they really started to correlate the ages and they started to match all the sedimentary horizons, they actually worked out, hang on a minute, all these glacial sediments from around the world were exactly the same age. And what was really neat about this was the fact that all these continents were actually, by using some more science called paleomagnetism, they were able to work out that these continents were also sitting on the equator, which is quite literally the very last place you would expect a glaciation. And so that kind of coined the discovery of the fact that these glaciers must have come down from the poles and met in the equator. And so I guess the entire Earth, for a moment, looked like a giant snowball. And so this is the idea of snowball Earth. The ramifications from the discovery of snowball Earth have been immense, and so they've been a really hot subject in scientific research, especially since it appears as though lots of factors in the world's ecosystems, in the world's composition changed, and out of the snowball it seems we got oxygen, it seems we got life. And so understanding this subject has been really important, and if it wasn't for understanding those fundamental stratigraphic principles, this discovery never would have happened.